Okay, this is the 11.6 video. Since it's your first video, I just want to go over a couple things real quick. Always before you start a video, you should have your book, some paper, something to write with, and your video sheet. And then in addition to having those four things, you need to have read all of the questions on the video sheet so that you know what you're looking for. And that way when you come to the answer of one of the questions, you will know, hey, that was one of the questions on the video sheet, and you can pause the video sheet and answer it. It's a lot easier to do it that way than to wait till the end and then have to go back and watch the video again because you couldn't find some of the answers. So if you are missing any of those four things, the book, paper, pencil, video sheet, pause the video, run get them. If you haven't already read the video sheet, pause the video and read it, and then you'll be ready to get started. All right, so 11.6, we're on page 638. We're going to start by talking about cylinders, and then we'll move into the quadratic surfaces. Here they have the definition of a cylinder. Most people, when they think of cylinder, they think of like a Coke can. That would be one particular kind of a cylinder. It's called a circular cylinder, but there are lots of other different kinds. And so basically what you're going to have in Cal C is you're going to have an equation that only has two variables. Like for instance here on page 639, y equals x squared, it only has x and y. The z is missing, and so what you're going to do is you're going to graph it two-dimensionally, and then you move it, in this case up and down, because the z is missing and the z-axis moves up and down. So you move it up and down, and that creates a three-dimensional surface. And so that's what cylinders do. So you can see this doesn't look anything like a Coke can, but that's going to be for the problems that it's just got two of the three variables. All right, and then quadratic surfaces are what most of the section is about. So the first quadratic surface we're going to look at is an ellipsoid. So an ellipsoid is basically a three-dimensional ellipse. It's formed by three ellipses. I don't know, what's the plural of ellipses? Anyway, there's three of them. So you can see here, you've got an ellipse here, and another ellipse here. So the three individual pieces of an ellipse, the three individual pieces of an ellipsoid are ellipses. I think it's ellipses is the plural. I don't know. And then here's another one. This is officially called a hyperbolic paraboloid. I call it a saddle because it looks like a saddle. These are very difficult to draw, so we're not going to do a whole lot of these, but you can see for a hyperbolic paraboloid, it's made up of two parabolas. Here's a blue one and the green one, and then a hyperbola. So that would be these red ones, it looks like. I can't even tell looking through my phone, but anyway, so it's hard to draw, but the picture, this is page 641. Here's just the general picture for it. For hyperbolic paraboloid. And then also on page 641 there was the ellipsoid. And then the rest of them, they don't have examples in the book for them, so I'll just show you here on page 641. You have an elliptic paraboloid. So an elliptic paraboloid in general is made up of two parabolas. You can see the blue and I guess red, and then an ellipse. That ellipse could be a circle, and same thing with the ellipsoid. On the ellipsoid, like this middle one could be a circle. So, but in general, they're ellipses. A specific kind of an ellipse is a circle. So if you just say ellipse, that covers ellipses and circles. So circles again is a special case. So in general, you would want to say ellipse, but these might be circles. Okay, so two parabolas and an ellipse is an elliptic paraboloid. An elliptical cone. You can't see it here in this picture. I'll show you in my notes in a minute. Here, all you really see are the ellipse on the top and the bottom, and then it looks like lines, but it's actually got hyperbola. So we'll come back to that one with a picture. But here is the hyperboloid of one sheet. So it is made up of two hyperbolas and an ellipse. This ellipse, they've just kind of drawn copies of it. So it's really just an ellipse and then a pair of hyperbolas. So two hyperbolas and an ellipse. It's a little misleading because they labeled all of these, but and then hyperboloid of two sheets, you've got an ellipse. And again, all of these ellipses might be circles, but just go with the generic ellipse to cover it all. And then also hyperbola. So there's several that are one ellipse and two hyperbolas. The difference is on this hyperboloid of two sheets, see how there's a gap between the pieces, but on the hyperboloid of one sheet, there's not. So we'll look at some examples and I'll show you how to tell when there's the gap and when there's not. But that's just kind of a brief overview of the 6 different types that we're going to look at. Now we'll look at them specifically with some problems. So these problems are on page 642. And the nice thing about these is they go ahead and give you all of the pictures and you're just really matching. But because I'm not going to do it for matching on the quiz or the test, here's how I'd rather you do it. I'd rather you don't look at these, so cover these up so you're not tempted to look. And then you're doing 1 through 12 all. So do it, graph it the way you think it looks, and then see if you can find it on here. And then if yours doesn't look very good, you can look at these pictures to see how it should have looked, and then go back and do the next one, graph it, see how you think it should look, then try to find it on here and adjust yours accordingly. So you'll do better on the quiz and the test if that's how you approach it. All right, so I'm going to show you some examples. I picked mine from the problems after 1 through 12. I'd hate to steal homework problems from you. Oh, before I forget, if you look in the Appendix 4, so this is kind of messy, but Appendix 4 pages, it's in the back of the book, AP 18 through AP 24. So there, I'll show you. See how in the back of the book they have crazy letters on stuff? So the Appendix Section, see how it has AP? So you've got, I don't even know what all these stand for, but you probably don't have that. That's even answers. This is an instructor's edition, so you probably don't have even answers. But anyway, there's odd answers, so just A's, and then the appendices. I don't know, plurals are not my thing. You have the AP pages, so that's at the back. So 18 to 24, if you need to review how to do an ellipse or a hyperbola, or parabolas for that matter, I think they're all back there. So conic sections are in the back of the book. If you need to review them, that's where you can find information about those. I'm just going to assume you know how to do them. And if you don't, then you're responsible for reviewing. Okay, we're going to look at number 16. So here's the way I would like for you to do these problems. I would like for you to do them. There's 3 two-dimensional pictures, and you do each of the 3 two-dimensional pictures individually. Then you put them all together to get the 1 3-dimensional picture. Okay, so that's how I like for you to do these. So first, let's look at, my pages are sticking. Okay, we're going to look in the XY plane. So in the XY plane, Z is 0. So what you would do is, of course it doesn't have it here, but you would go up to this equation. If there was a Z, you would plug in a 0 for the Z, and then you would get this equation. All right, so then you want, this is an ellipse, you want to get it equal to 1, so you divide everything through by 36 and you get this. So it's an ellipse. The x-intercept is plus and minus the square root of 9, which is 3. Y-intercept plus and minus the square root of 36, which is 6. So here's your intercepts. All right. Now, next, in the xz plane, y is missing, so y is 0. Go back up here, plug in a 0 for the y. It becomes this equation. Divide by 4. Take the square root of both sides. Don't forget the plus or minus. And notice that's lines. Okay, so you have lines. And then in the YZ plane, you have x is missing. I mean, x is 0. Sorry, x is 0. And so you would go up here and plug in a 0 for the x. That gives you this. Take the square root of both sides. It's more lines. So this one, you didn't actually have to do it this way. I'm going to show you a better way to do this one. This one is one of the cylinders. It is not a one of the quadratic surface ones. So I'll show you a different way to do this one. But to introduce the way we're going to do the quadratic surfaces, I did it this way so you could see that you can do them all this way. But the cylinders are a little bit easier, so you could do it a faster way on the ones that are cylinders. But anyway, notice this is an elliptical cylinder, not a circular cylinder. So in the XY plane, what you could have done the ellipse. So see, notice how here the Z was missing. So you could have just done the ellipse in the XY plane. That's this one here. And then, because the Z is free, in the original problem there were no Z's, you would just take that ellipse, and because the Z-axis moves up and down, you take that ellipse and you just slide it up and down like this, and that makes this this cylinder. Okay, so that's how you could have done it because it was a cylinder. So if you only have 2 of the 3 variables, then you can do it the shortcut way. Because it's a cylinder, you just graph it in the 2-dimensional plane that corresponds to whatever 2 letters you have, and then you just move it up and down if the Z is missing, or front and back if the X is missing, or right and left if the Y is missing. Okay, so that's what it'll look like. So you do need to make these look 3-dimensional. If you were going to graph it from what I had, you have the ellipse, that's here. These lines, X equals plus and minus 3. They, in general, they would be planes in the 3-dimensional coordinate system, but here, because I'm in just the XY plane, if I'm just in a plane, then this is just a line. So just in case that was confusing, it's because I'm in a plane. So that would be here and there. And then the Y equals plus and minus 6, again, just in the YZ plane, that's lines. That would be here and here. So it's what gives the the height to the cylinder. Okay, so that one, there's two different ways to do it, and that's true in general for cylinders. Okay, so let's look now at number 20. Notice number 20 is not a cylinder because see how none of the variables are missing. So again, just in case this was confusing, if it's a cylinder, one of the variables will be missing. You can go straight to here, draw the two-dimensional picture, and then just move it the way the missing variable, its axis moves. But if all three variables are there, then you'll need to do it with the three two-dimensional pictures. All right, so here we go. Let's move this paper so we just look at one at a time. My dog is making all kinds of racket. I don't know if you can hear her in the background, but my dog is making noise. Hopefully you can't hear her. Huh. You're lucky because it's annoying. She drives me nuts. Okay, in the XY plane, Z is 0. Whoops, let me uncover that. Okay, Z is 0 in the XY plane. So put a 0 for the Z. You get this. Divide by 36. You get this. It's another ellipse. X-intercept plus or minus the square root, Y-intercept plus or minus this square root. So I get these. All right, hold on. Now, in the XZ plane, the Y is 0. Put a 0 in place of the Y, you have this. Divide by 36, you get this. Another ellipse. X-intercepts plus or minus the square root of this number. Notice here this denominator, it's not written, but it's a 1. So plus or minus the square root of 1, that would be the Z-intercepts. And then lastly, in the YZ plane, X is 0, plug a 0 in for the X, you get this, divide by 36, another ellipse, here's the intercepts. So 3 ellipses, that's an ellipsoid, and an ellipsoid is made up of 3 ellipses, whatever. I'm going to call them ellipses. I don't because this is not grammar, this is calculus, so who cares? Okay, so football shaped, appropriate for the fact that football season is starting soon. Hooray, hooray. All right, so here's my intercepts on the Y, plus or minus 3, on the X, plus or minus 2, on the Z, well, I didn't label the 1, but plus or minus 1. There's a negative 1. All right, so that's an ellipse. So again, you have to make them look three-dimensional. They don't have to be beautiful, but they have to be three-dimensional. All right, moving on. Let's try another one. All right, so here, notice again, all 3 variables are present, so it's not a cylinder, so you do need to do it with the 3 two-dimensional pictures. So let's look at these one at a time. And since we've done several of these, I'm going to go through this a little faster. Here Z is 0, so when you replace the Z equals 0 and move everything over, notice that's a circle, not an ellipse, it's a circle. And the center would be the origin, radius square root of 8, which is, I don't know, roughly, what, 2.8, something like that, a little less than 3. In the XZ plane, Y is 0, so now it's a parabola. It is opening down and shifted up 8 units. And then in the YZ plane, X is 0, another parabola, again opening down, again shifted up 8 units. So you have 2 parabolas and a circle. In general, 2 parabolas and an ellipse make the elliptic paraboloid. So this would actually be a circular paraboloid because it has a circle. Elliptical is just in general, circular is a specific case, but if it asked what was it made up of, in general, 2 parabolas and an ellipse, sometimes 2 parabolas and a circle. Okay, so this is it. You've got the 2 parabolas. There's one, there's the other one. Opening down, shifted up 8 units. You've got the circle in the XY plane. It does keep going down below this. I just stopped drawing it when I hit the XY plane, but it does keep going down. So that would be, in general, an elliptical paraboloid, but here it's specifically a circular one. All right, next, 28. So here again, all 3 variables. So we're going to do the 3 two-dimensional pictures. I'm not going to cover them up this time. It's too much of a pain to keep both papers. All right, XY plane. This is a hyperbola. Again, if you can't tell the difference between a circle, a parabola, a hyperbola, or an ellipse, you need to spend some time in that appendix. So this is a hyperbola. Hopefully you learned this in trig, if that helps jog your memory at all. Conic sections in trig, which would have been 113 or 115, depending on what you took. So the hyperbola opening about the y-axis, since that one's the positive, the intercepts are plus or minus 1. In the XZ plane, another hyperbola, this time opening around the z-axis, because that's the positive one. Intercepts also plus or minus 1. And then when x is 0, you get a circle centered at the origin, radius 1. So this one, and I'll show you how to tell whether it's a hyperboloid of 1 sheet or a hyperboloid of 2 sheets when we get to the hyperboloid of 2 sheets. It's not going to make sense if I tell you right But this is a hyperboloid of one sheet. So in general, a hyperboloid of one sheet is hyperbola, hyperbola, ellipse. This is a special case where it's a circle, but in general, hyperbola, hyperbola, ellipse. Okay, for hyperboloid of one sheet. So I am really bad at drawing these. So I only actually drew one set of the hyperbolas. See that? That's one of the two hyperbolas. And then here's the circle here in the center. And then as it goes out, the radius of the circle is getting bigger. I didn't draw the second set, but they would be here and under there. It's the under there that I have trouble drawing. So you don't have to get both sets of hyperbolas on there, but there is another one, you know, coming here to the middle and out and then underneath. I just, I can't ever make it look good, so I finally just gave up. All right, that's the hyperboloid of one sheet. Okay, moving along. I'm trying to do one of all 6 plus a cylinder, so 7 examples in case you're wondering, is this ever going to end? Eventually, yes, it is going to end, just not yet. Okay, this is the saddle. I'm not going to give you any of these on a quiz or a test. I'm just giving you, I think, hold on before I lie to you. Okay, there's 2 on the homework, just because it's, you know, 1 through 12, and they're K, my chair is squeaky, K and L are saddles. So I did give it to you for the homework, just in case. I don't know if you're going to need this in another class, so I want you to be exposed to it. But because they're notoriously hard to draw, I'm not going to give it to you on a quiz or a test. But just do it for the homework. Okay, so here's the equation. And then notice what happens here. In the xy plane, it's lines, right? If z is 0, because this is squared and this is squared, if you take the plus or minus of both sides, it's lines. However, as soon as you move away from z equals 0, so if you move either up off the xy plane or down below the xy plane, as soon as you move. So here I've moved 1 up from the xy plane. Notice now all of a sudden it's hyperbola. So that happens a lot, that in one value for z it's lines, every other value for z it's hyperbolas. And so this is the first time you've seen it, and this is in the saddles. But notice those hyperbolas, when you draw them, they are at z equals 1. So they're up off of the xy plane, because in the xy plane they'd be lines. All right, so here you have parabola, here you have parabola. So here's what it looks like. I don't know if you can tell from that picture. They're really hard to draw, which is, again, is why I'm not going to give it to you for quizzes or tests. And then for the homework, you can see they're already drawn for you. So just do your best, and then you can figure out which one it matches up with. But you know, if you can't pull these off, it's okay. Just, you know, do the 3 two-dimensional. I didn't even draw the pictures. Why did I not draw the 3 two-dimensional pictures? How terrible of me. I'm so sorry. I just totally robbed you. I robbed you of that opportunity to see those pictures. I don't know why they're not on my notes. I'm so sorry. Okay, but I can't pause the video because, well, I just can't. And so I'm not going to do it now. So I'm so sorry that I robbed you of that learning opportunity on this. Number 32, so sorry. Okay, moving along. Number 40. This is, well, I'm not going to ruin it and tell you what it is, but this is the next picture. I don't know if you noticed which one we haven't seen yet. Didn't even know what it was, but let's not ruin the surprise. Okay, watch what happens. In the XY plane, you get lines. In the XZ plane, you get lines. Now, watch out, because in the YZ plane, and this is not necessarily always the YZ plane, but it happens in one of the 3 planes, okay, not necessarily the YZ plane. So in this specific case, in the YZ plane, x equals 0, this is what I get for my equation. This is always positive, this is always positive. I'm adding them together. The only way that's going to be 0 is if both of those are 0. So in other words, y and z has to be 0. Y and z have to be, whatever. This is not grammar. X was already 0, so that would have to be the origin, which means it is a dot. It is a dot. That's not very helpful to you. A dot is not helpful. So try something else. Try x equals 1. So move forward 1 unit, see what happens. So plug in a 1 instead, and you get this, which is a ellipse. Okay, so you get an ellipse. Notice that for the intercepts, because I'm in the x equals 1 plane, my intercepts are at 1 for the x, not at 0. Okay, so you have to be really careful. All right, now I also didn't do it here. I don't know what my deal is. I guess I was getting tired of drawing. I didn't draw the pictures on this one either. Here, if you tried something other than 0 for these 2, instead of lines, it's going to happen like up here. you're going to get hyperbolas. And so they are lines for one particular value and hyperbolas for everything else. The same thing happens here. Okay, so what you get is a cone. So for the cone, you can think about it one of two ways, whichever way makes more sense to you. A cone, you can think about it as being made up of lines, and an ellipse, or lines for this one special case and then hyperbolas for everything else, lines for this one special case and then hyperbolas for everything else, an ellipse. So whatever makes more sense to you. But notice the difference. Where did it go? Hold on, just a second. Okay, notice in the, hyperboloid of one sheet, hyperboloid of two sheets, okay, there's my S, and cones are easy to mix up. They're easy to mix up. So I'm going to show you how to tell the difference. We'll get to the hyperboloids of two sheets in the next example. But between hyperboloids of one sheets and cones, I'm going to tell you how to tell the difference. In a hyperboloid of one sheet, in the middle is a circle or an ellipse. Okay, if in the very middle of it, you're going to get, like here, a circle, or in general, an ellipse. But in a cone, in the very middle of it, you're going to get a point, like here how it happened with the origin. So that's how you can tell. If you get a point, a single point, then it's going to be the cone. If you get a circle or an ellipse in the middle, then it's a hyperboloid of one sheet. So both of them, another way you can tell, see how these are hyperbolas? If I picked other values here for z and y, they would be hyperbolas. So it would be hyperbolas and hyperbolas. But this one is going to give you lines for one special case, z equals 0 and y equals 0. And then hyperbolas for everything else. This one's just always going to give you hyperbolas. That's another way to tell. Okay, so I forgot to mention this up here on the saddles, which are officially called hyperbolic paraboloids. That was made up of a hyperbola, parabola, just in case I didn't already say that. Okay, so again, on the cone, you can think about it as lines, and ellipses, or you can think about it as lines/hyperbolas, ellipses. Okay, and last but certainly not least, this is the only one left, so I'm going to just ruin the surprise and tell you what it is. It is a hyperboloid of two sheets. Or they look like contact lenses, I think. Okay, so here we go. In one of the planes, you're going to get hyperbolas. In another plane, you're going to get hyperbolas. Now here's the weird thing, and this is how you're going to be able to tell the difference between the hyperboloid of two sheets versus the hyperboloid of one sheet. If you try to pick a certain value, which typically for these problems is going to be when you try to pick 0. If you try to pick 0, notice what happens. That's not possible because this x squared is always positive and then you negate it, or 0. Z squared is always positive or 0 and then you negate it. You're never going to be able to put that together and get a 1. That's just not going to happen. So if you try y equals 1. If you try y equals 1, I did that work up here. If you try y equals 1, see how this is that same situation that happened before? It's just a point. So if you try y equals 0, doesn't work. Y equals 1, just a point. Y equals square root of 2, and I did square root of 2 for a reason. You'll see when it works out, because it works out nicely for my radius. So if y is the square root of 2, when I plug that in, then the square root of 2 squared becomes 2. Move it over, circle, centered, not at the origin, because this is different, but 0, 0 for x and z, radius 1. But because the y was the square root of 2, then for the center, instead of it being 0, it's the square root of 2, because that's what the y was. All right, so notice what happened. Here's this little note. You can pause it and read it in a second. I'm not going to read it to you. That's boring. But notice what happened. See, in here, when I tried to pick y equals 0, it didn't work because that's the gap between the two pieces of the two sheets, right? There's the two contact lens pieces. They don't touch. And so because they don't touch, you've got this gap. And so if you try to pick anything between -1 and 1, you're in that gap and it's not going to work. But then if you try to pick y equals 1 or y equals -1, you're just going to get a dot. And I did them in pencil. I don't know. Let's see if you can focus. Okay. See in pencil? That's the dot, y equals 1. That's the dot, y equals -1. Then as you move out for any other y values, like I picked square root of 2, then you're going to get these circles. In general, ellipses, but here, circles. And so that's how you can tell it's a hyperboloid of two sheets, because when you try to pick 0 in general, it's not going to work, right? So that's how you can tell if it doesn't work, because there's a gap in the middle. So this one is made up of hyperbola, and then in general an ellipse, specifically here, circle. So just to recap the three that are easily mixed up, I'll put them all here together. This one in the middle, you're going to get a circle or an ellipse. This one in the middle, you're going to get a dot. This one in the middle, it's not going to work. It's going to be a gap. Okay, so those are all easily mixed up because like if you look at this hyperboloid of one sheet, see how it's hyperbola, hyperbola, in general, an ellipse, here a circle. And then here it's, for the hyperbola of two sheets, hyperbola, hyperbola, in general, an ellipse, here a circle. And then here, if I picked other values, which I didn't, but if I had picked other values, it would be hyperbola, hyperbola, ellipse, or circle. So see, they're all easily confused. But again, on the cone, you're going to get lines for typically when you pick 0. And then here you're going to get the gap. Here you're going to get the point. Here you're going to get the circle. So that's all the ways you can tell them apart. So that's all 6 of them plus a bonus cylinder. And so if you need to see any more examples, there's 2 more examples in your book. And then you're going to be working on these 1 through 12 for homework. So just to show you, to make sure you understand what these are, notice these 2 are cylinders, okay? Ellipsoids, elliptical paraboloids, cones, hyperboloids of one sheet, and I keep wanting to say saddles, hyperbolic paraboloids. I don't know why, but they don't have hyperboloids of 2 sheets for some reason. They don't have those on here. So unfortunately, you don't get to practice with those in the 1 through 12. I'll, hold on, let me write myself a note. Note to self, find hyperboloids of 2 sheets. So I'm assuming in this assorted section, there's probably some. Now, okay, people always ask me, can't I just memorize the formulas and see what they are supposed to look like? Sure, if you want to, knock yourself out. But I'm still going to ask you for the 3 2-dimensional pictures, so you may as well just do it with the 3 2-dimensional pictures and don't waste all that time trying to memorize. So had I memorized what the hyperboloid of 2 sheets looked like, it looks like one of them squared and 2 of them are minus. So if you see something like that in here, in the assorted, I'm just going to find some later. I don't want to think about it right now, but I'll find some later for the hyperboloids of 2 sheets and tell you what problems they are, and that way you can practice with some of them. But what you need to do now is go back through your video sheet, see if there was anything you missed. Some of the stuff is in the book, some of the stuff is only in the video. Make sure to fill out the whole video sheet. A lot of times people skip certain questions because they just didn't notice them or see them or something. So go back through, make sure you didn't skip any of the questions, make sure to answer them all, and then you're going to bring it to class with you next class and turn it in. So don't forget to bring it with you, and then we'll work on the homework in class. So if you have any questions, send me an email. My email's on the syllabus, and if not, I'll just see you in class.